Good morning. I'm pleased to present our research titled Using SSP-TOPSIS in Sustainable Resource Selection for Mobile Cloud Computing. This work is a collaboration between researchers from the University of Szczecin and the West Pomeranian University of Technology. We focus on improving sustainability decision-making, especially in selecting smart mobile devices in mobile cloud computing. The proposed approach addresses limitations in classic multi-criteria decision analysis models, namely linear criteria compensation, which is inconsistent with the strong sustainability paradigm. In this paper, we propose a multi-criteria approach called the strong sustainability paradigm-based technique for order preference by similarity to ideal solution, SSP-TOPSIS method, which enhances the well-established TOPSIS method. This enhancement allows for modeling the degree of linear compensation reduction among criteria, thereby adapting compensatory MCDA methods for evaluating multi-criteria problems within the context of the strong sustainability paradigm. The presented method was used for a practical example of smart mobile devices for mobile cloud computing selection. Smart mobile devices, namely smartphones and tablets, offer significant computing capabilities. They are often preferred by users over laptops and desktops. These devices possess substantial computing resources that can be utilized by applications requiring additional processing power for compute-intensive tasks when they are not in use by their owners. Public smart mobile devices, whose owners have agreed to make their computing resources available, can be employed as computing resources in mobile cloud computing, effectively creating a mobile cloud computing. The first step of SSP-TOPSIS incorporates building a two-dimensional decision matrix, including performance values collected for the considered variance. In the second step, we have to calculate the mean deviation for each performance value included in the decision matrix. It is performed by subtracting the mean value from performance values for each criterion. Then multiply the outcome by the sustainability coefficient S, which is an adjustable parameter of the SSP-TOPSIS method. Sustainability coefficient represents the rate of compensation reduction in particular criteria. Values of the sustainability coefficient can be assigned by the decision maker individually for each criterion as real values ranging from 0 to 1. The whole procedure of the second step is performed with the presented equation. In step 3, we have to assign 0 values to these mean deviation values for profit criteria that are lower than 0. If mean deviation values for profit criteria are lower than 0, it denotes that performance values for profit criteria in the decision matrix are lower than their mean value. We also have to assign 0 values for these mean deviation values for cost criteria that are higher than 0. It means that performance values for cost criteria in the decision matrix are higher than their mean values. This step is intended to prevent undesirable improvement of performance values that are outliers from the mean toward the worse. Step 4 incorporates subtracting mean deviation values from performance values included in the decision matrix. The remaining steps are analogous to the classic TOPSIS method. Step 5 involves normalization of the decision matrix. We can choose the minimum-maximum normalization, which is useful because it can be applied in the case of negative value occurrences. Step 6 involves calculating the weighted normalized decision matrix. It is performed by multiplying the normalized matrix by appropriate weight values. In step 7, we have to determine reference solutions, including the positive ideal solution and the negative ideal solution. Step 8 involves the calculation of the Euclidean distance of evaluated alternatives from reference solutions determined in the previous step. In step 9, closeness coefficient values for evaluated variance are calculated. Finally, variants are ranked by sorting their closeness coefficient scores in decreasing order. Smart mobile devices' computing resources are specified by the criteria used for selection listed based on the reference research paper cited on the presented slide. Choosing smart mobile devices based on their parameters, which often conflict with one another, can be complex. Additionally, these parameters are not interchangeable, as each one serves a specific function. The multi-criteria problem of selecting smart mobile devices for mobile cloud computing necessitates a preference for sustainable alternatives while adhering to the principles of the strong sustainability paradigm. This approach emphasizes the need to limit the linear compensation of criteria. Linear compensation implies that excellent values achieved for several criteria can compensate for poor values in other criteria. It is undesirable when searching for balanced alternatives, which should achieve good values for as many criteria as possible. A dataset has been utilized to demonstrate the application of the SSP-TOPSIS method for selecting the most sustainable alternative smart mobile devices for mobile cloud computing. This dataset, along with the evaluation criteria, is derived from the reference research paper cited on the presented slide. In the first stage of the research, a linear compensation reduction approach is applied within each group of smart mobile devices parameters that serve as evaluation criteria. The analysis was conducted for the following 4 groups of criteria. Criterion C8 has not been assigned to any group, but has been included in the final scenario that considers the reduction of compensation across all parameters. Then we have performed a sensitivity analysis with increasing S coefficient for particular parameter groups. Next, we have conducted a comparative analysis of SSP-TOPSIS with reference multi-criteria decision analysis methods. 2 methods with limited compensation, PROSA-C and Promethe-2, and 1 compensation method, classic TOPSIS. Comparative analysis was carried out in 2 scenarios for constant and increasing values of the sustainability coefficient. In the first stage of the research, sustainability coefficient was set as a standard deviation value based on the decision matrix. The column titled None contains results for a scenario without compensation reduction for any criterion, which is analogous to the classic TOPSIS method. On the other hand, the column called All includes results for compensation reduction in all parameters. It is evident that, regardless of the evaluated parameter group with reduced compensation levels, the highest rated alternative is consistently A9. This observation indicates that the device performs favorably across most of the considered criteria, allowing it to achieve good evaluation results even when compensation possibilities in certain parameter groups are limited. The alternative A8 achieved 3rd place in all analyzed parameter groups, with the exception of the battery parameters and the group considering all parameters. When the criteria compensation was reduced in these 2 groups, A8 dropped to 4th place. This change occurred because A8 exhibited the most favorable values for the battery capacity, battery temperature, and one of the most favorable values for the battery availability parameters. Reducing compensation in these groups limited the ability to compensate weaker values in the other criteria, resulting in a lower score for A8 compared to scenarios where compensation was not reduced or adjusted for the other parameter groups. Similar conclusions can be drawn for the other alternatives included in the investigation. The next stage of the investigation involves increasing the sustainability coefficient for each parameter group within the range of real numbers from 0 to 1. A value of 0 indicates no reduction in compensation at all, while a value of 1 means a maximum reduction in compensation. The graphs indicate that alternative A9, which was the leader in the first stage of the study, maintains its leading position during increasing compensation reduction across all criteria groups. This suggests that alternative A9 is sustainable, as its performance across all parameters contributes to its top ranking. Alternative A10 also demonstrates sustainability, consistently securing a stable 2nd place in the rankings, with the exception of scenarios involving high compensation reduction across all criteria. One example of an alternative that demonstrates a declining trend due to an increasing reduction in criteria compensation is A8. When we consider the parameters of CPU, GPU, battery, and memory within each group of criteria, A8 falls from 3rd to 4th place as compensation reduction increases. Conversely, when looking at all parameters collectively, A8 drops by 4 positions, falling from 3rd to 7th place. This indicates that there is a lack of sufficiently favorable performance values across a wide range of parameters, which would normally help this option secure a stable and high ranking, even with decreasing compensation for the criteria. The alternative that demonstrates significant potential for improvement, particularly with a decreasing criteria, compensation, is A5. In summary, the analysis clearly indicates that the most preferred and sustainable smart mobile device option among those considered is A9. The next step of the research was an empirical comparison of the SSP-TOPSIS method with two other methods constraining compensation, namely Promethe-2 and Process-C. Displayed figure shows the convergence of the SSP-TOPSIS ranking generated using a sustainability coefficient E set as 0.6 for all considered parameters, with the rankings of the TOPSIS compensation method and the two compensation limiting methods, Promethe-2 and Process-C, for which the value of the coefficient S was set to 0.3. The weighted Spearman correlation coefficient was used as a measure of ranking convergence. It can be noted that the SSP-TOPSIS and TOPSIS rankings differ because, although their correlation is high, 0.9152, it is lower than 1, which indicates the existence of differences resulting from the reduction of compensation by SSP-TOPSIS. On the other hand, although the Promethe-2 ranking is less consistent with SSP-TOPSIS compared to TOPSIS, which results from differences in algorithms, the correlation value between SSP-TOPSIS and Promethe-2 is still high. Particularly noteworthy is the correlation between the SSP-TOPSIS and Process-C rankings, 0.9636, which is higher than that between TOPSIS and Process-C, 0.8920, and between SSP-TOPSIS and TOPSIS. This means that the SSP-TOPSIS method reduces compensation to a greater extent, giving results similar to other methods with limited compensation like Process-C. Then research was conducted on the correlation between the SSP-TOPSIS ranking and TOPSIS, Promethe-2, and Process-C for increasing values of the sustainability coefficient in SSP-TOPSIS. It can be observed that as compensation in SSP-TOPSIS decreases, the correlation with the compensatory TOPSIS method decreases. In contrast, in the case of Process-C, the correlation with SSP-TOPSIS increases, especially for the sustainability coefficient from 0.4 to 0.7. For larger values of the sustainability coefficient, the correlation between SSP-TOPSIS and Process-C decreases. However, it is higher than for TOPSIS, which confirms the ability of the SSP-TOPSIS method to reduce compensation. This research demonstrated the method's effectiveness in addressing multi-criteria selection problems for SMDs within the context of MCC. The integration of compensation reduction modeling enhances the analytical capabilities of the traditional TOPSIS method, allowing for the identification of more sustainable solutions. Future work should focus on enhancing the model by including additional evaluation criteria, utilizing a broader dataset with more alternatives, and expanding other multi-criteria methods to support compensation reduction modeling capabilities. This work was supported by the Polish National Science Center and the Ministry of Science. Thank you for your attention.